So welcome everybody to the next one in our PSDI webinar series. So today we are going to be hearing from Samuel Monday from Data Revival, making the intangible tangible, the journey from lab notebook to digital insight. So without further ado, I will stop my screen share and I'll hand over to you, Sam.
Thank you very much, Nikki. So welcome everybody. Thank you very much for coming. Today, I'm going to be talking to you about some of the work that I've been doing with sort of two hats on. So one hat is within the academic sphere, and the other hat is commercializing some of the research and the platform that we're creating. And it's all about, well, as it kind of says in the title, making the intangible tangible. So all of that rich scientific chemical knowledge that sort of sat in lab notebooks on bookshelves, or it sat in PDF files never being looked at. Can we build something and can we do something with that that makes sense in a digital world, or in a modern world where we're trying to use digital methods on all sorts? But before that, who am I? So as Nikki sort of introduced me, my name is Sam Monday. I am a research assistant at the University of Southampton, and I work in Professor Jeremy Frey's group in the chemistry department. We don't really do that much of what you might class as stereotypical chemistry, in inverted commas. We mostly look at data, software, research methods, sort of how can we apply all of these computational methods to the area of chemistry. And that's really why I put there that I have a background in developing analytic systems for chemical systems, because a lot of my job historically has been putting data together and building machine learning models to try and do predictive analytics on some chemical system. And that's sort of one hat. And then my other hat, sort of part-time, is I'm the co-director of Data Revival. And Data Revival is the company that Jeremy and I have created. And we're in the process, we're very new, very young, but we're in the process of spinning out some of the technology that we've built, and I'll be talking about today, into that company. And it's going reasonably well at this early stage. We've got a couple of big commercial clients, and we've got a bit of innovate money behind us. So it's all looking pretty rosy at the moment. So just before I launch into what the talk's about, just a little bit about Data Revival, because it is intrinsically linked to the technology that I'll be talking about. But our whole idea was, well, as I've sort of said, can we take that chemical knowledge, all that vast decades and decades of written down work from the lab notebooks, from the bookshelves, from the filing cabinets, and can we develop a system that can extract that information in a way that makes sense for scientists, or for chemists in this instance? And can we connect all the dots? Can we connect that knowledge across maybe geographical locations, or can we connect the dots through different or similar areas of chemistry, or across people? And then once we've done that, can we structure that information in a way that makes sense for what people want to do with it today? So can we structure it in a way that works nicely with databases or ELNs, or just search, or maybe they just literally want to be able to put it into their database and sit on it so that it's out the way, maybe not a fire risk anymore. And the idea here really is, we'd love to make this knowledge available so that people can do with it whatever they'd like, but in a modern way. And so how did I sort of end up here? Well, as I mentioned, I am part of the Frey group, and they've done an awful lot in the past about e-science, digital chemistry. I think in the early 2000s, they were working even on electronic lab notebooks and better research data management. And so I sort of came into this group that's spent an awful lot of time looking at how we can use data better in the chemical lab, or in chemistry as a whole. And it sort of dawned on us that actually what that means is we're always trying to fix the future. We're always saying that we need to digitalize, we need to use better machine learning models, we need to improve our metadata collection going forwards, or we need to do better with ELNs. And actually, we focus so much on fixing the future that I don't really think that many people, in the way that we're approaching it, have focused on trying to fix the past. And so that's where we really came from this. How much data exists, or knowledge exists out there, that we're kind of forgetting about at the moment because we're focused so much on implementing those new digital methods. And then me personally, I really came into this whilst I was in a collaboration with a large chemical company in the UK. And they wanted to be able to predict the properties of their materials before they even got to the lab. And so sort of young, arrogant, early 20-something me thought, easy, get me in there, we'll bang a linear regression on it and everything will be rosy. But what we very quickly realized, and I'm sure lots of people in this call will have seen this problem, is that you might have decades and decades and decades of world-leading research, as this company did, but very little of it actually played nicely with me wanting to put it in a linear regression. And there was just a gold mine of knowledge buried in their lab notebooks. And so all these things sort of came together and we said, okay, right, what can we do about this? What tools do we need to build? And so we started off at home in Southampton University. And that's a picture there of Mansour. He's a really great chap, works in our department. And I was chatting to him one day about these sorts of problems and what we were thinking of doing. And he said, Sam, I've got the perfect project. And he said, follow me. I want to show you a cupboard. And that was all he sort of said to me. And I thought, well, never want to turn down a mysterious opportunity. I sort of followed him along to this cupboard. And you'll see there that Mansour is about average height. And that is a cupboard full of lab notebooks. It goes up way beyond the height of the door frame and it goes back 2 or 3 meters. It's a humongous cupboard. And those boxes just all haphazardly stacked in there, full of lab notebooks. We estimate, even now we don't know how many are there. We estimate about 3,000 or 4,000 of them, with a sort of very finger in the air, 2,000 chemist years worth of work. But he said that, look, these have been sat here. Actually, they've moved around various different cupboards, but these have been sat here for an awful long time, doing nothing, essentially wasted. And he said, I think this would be a great place for you to start. And so that's what we did. And we thought, well, what's the first thing that we need to do? Well, we need to digitize them. Not exactly the most exciting thing in the world, but actually we thought, right, let's sit down and why do we need to digitize them? Would it be better just to offload all of these to the library, put a nice little tag on them, have them, the metadata of them put into some sort of database so that people can go to the library and find them? But we thought, actually, there are 3 broad reasons why we wanted to do this digitization. Obviously, from a practical standpoint, we wanted to free up the cupboard space. We wanted to remove the fire and flood risk. This was a genuine concern of Mansour's. Not just that they might set on fire, but if they did set on fire, and let's say we do have 2,000 chemist years worth of work, that'd be a great shame to lose all of that. And the other part about digitizing them is that we found that we started to have people come out the woodwork and want to give us their lab notebooks. So it wasn't just the ones that we found in that cupboard, ones that were sitting on someone's desk for a few years or on their bookshelves. And they've started filtering in. And I'm sure my colleagues at Southampton can tell you that I am building a bit of a lab notebook fortress out of the number of notebooks that are just sort of piling in because people have heard about this process that's going on. There was also some compliance things in there, so health and safety. There was a hell of a lot of COSH forms in there that nobody really knew about. If something had gone wrong in the future, or if something had gone wrong in the past and we were only hearing about it now, it was going to be impossible to look through all of the information about what that person had done, what safety precautions were in place and things like that. The longevity of records, so I don't know whether there might be IP situations in the future, but certainly nobody was going to be able to look back through them. And actually, some of the notebooks at the bottom were starting to get damaged beyond repair. So even if the information did exist, it was starting to degrade so that we might not be able to find it. And then the obvious one, productivity. We really wanted to make them searchable, findable, accessible. We wanted to be able to mine the data out of them and use AI and ML and throw all the buzzwords at them. So we started this process of scanning and we engaged Southampton University Library. And we very quickly realized that this was going to be a monumental task to undertake. However, the guys at the library are brilliant and they're very professional and they've just been methodically going through the scanning over the last 18 months. And we've managed to think, I've got 430 notebooks definitely scanned. And I think the next batch is just about to come in. So we'll have about 500 scanned in. But I just thought I'd put a picture of the scanner that we've been using here because some people on this call may be familiar with them, but some may not. And the very top there is the camera to scan down from. Then you have a glass tray that you activate with foot pedals that can come down onto your book to flatten it off. You'll see that there is in the middle here, 2 leveling plates so that you can auto level no matter the thickness of the spine of the book. and that should give you a flat scan. And the process really is put your book in, get some black cardboard because you want to put it below the page so you don't get bleed through, and you want to put it over the other page so that you only scan one page at once. You then have to press the buttons to get it to auto level and lock it in place, bring down the screen, go to the computer, press a load of buttons and take your scan. And invariably it's probably skewed or off center or something like that, and you have to go through that process. So actually, in doing this type of scanning, we were getting very, very good scans, which I'll show you later on in the talk, but actually it was taking a huge amount of time. And one of the reasons that it was taking so long is that every time there's an insert, you've got to take the insert out. So it might be stapled in, it might be paper clipped in, they definitely have to come out. The ones that are glued in are the worst because it's very difficult to remove them from the book, and then it's very difficult to stop bleed through coming through from the page below, or at least in my experience. And then you also have sellotape that you might have to take out as well. And then when you take these inserts out, or the things that have been inputted, often you are adding to the number of pages in the book. So a 200-page lab book very quickly becomes 250, 300 scans, and you have to scan them separately. And I thought I'd just put a couple of up-close photos because it's not the most interesting thing in the world, but actually I never knew scanners got this complex. And these are some of the books, some of the pages, sorry, that we have scanned in. And you'll see actually that, I don't know if this is surprising, but it was certainly maybe slightly surprising to me, they're absolutely brilliant. They are great representations of the physical asset. So we can see here that they're human readable, and I'll talk about later on in the talk how they're also machine readable. They are flat, they're straight, the quality is really, really good. And actually, we've gone through this process of manually scanning, and now we're having a chat around, well, can we destroy the old lab notebooks? Can we literally just get rid of them because we have these amazing digital versions here? And that's a conversation that's going on at the moment. The other thing, just before I move away from this absolutely riveting topic of how we scanned them all in, is we started with the professional versions, and we're now migrating towards this Microsoft scanning. So we're trying to scan in 10 or X number of thousand notebooks, but it may be that you only have 2 or 3. And the Microsoft scanning app is absolutely phenomenal. You still have to put the black pieces of card under and over the pages, but actually from your phone, you can take really, really good high quality scans that are good enough. And unfortunately, I didn't have an example of a page with lots of information on it, but you can see, okay, this isn't quite as good because it's got that sort of curve, that ridge in there, but it's still pretty straight. And the fact of the matter is that this is still human readable and it's still machine readable. So I think if you only have a few lab notebooks, scanning them in this way is actually a really useful and good way to digitize your work. The reason I've sort of mentioned both is because of the time considerations. A single page on average takes around 45 seconds to scan with the professional stuff. When you average that out over 10 pages or more, actually that goes up to over a minute per page. And you'll see later that we've got around 230,000 pages that we need to scan. So it's a hell of a lot of time just to get them in. Whereas if you use the Microsoft scanning app, that goes down to around 10 seconds per page on average. So far, far, far faster. And just to sort of start rounding off this section, we've scanned around 430 notebooks. We've got maybe 2 and a bit thousand to go. And as I've said, that equates to, I think we've scanned in something like 22,000 or 26,000 pages. And we think there's just under 250,000 pages here. And I think they're really interesting stats because that's 250,000 pages that people have written stuff down on that were literally just sitting in a cupboard going dusty and doing nothing. So what did we learn from all of this? Well, actually, if you want to digitize your work to send it into a platform like we're building, the quality doesn't need to be as high as you think. We started off with, I think, 600 DPI. So humongous file sizes and qualities and for each of the images of the pages. But actually, when they run through our platform, we reduce the quality by about 90%. And the human readability of those scans doesn't particularly degrade that much, and our models deal with it absolutely fine. And again, on that note, straight and flat is better, but not essential. It's bleed through that's the real killer. And if you start digging back through your archives of sort of PhD students' lab notebooks, you'll find that a lot of them have very little in or some very poor quality layouts and chemistry going on in them. Storage is a massive thing here. We are looking at 12 terabytes of storage for all of these lab notebook scans. And this is storage that's going to have to persist over 20, 30, 40 years. Easy to say. There are, we do have services in place to do that, but still a consideration. To do any of the machine learning or mining or things like this, you need to have smaller, faster access storage. I'm sure we're all aware of how the tech stack has to work here. And I put here integration with everything else. When we first started this, we didn't really set it up so that the database of the pages would play nicely with the cluster that we were working with and all of this. So, really have to think about integration. And then I'm sure some of you are sort of sat at your screen screaming at me, well, you can do this automatically. You can destroy these books, you can chop the bindings off, and then you can feed them through a machine that will just churn through everything. And that is absolutely true. But we needed to go, two things here. We needed to go through that process of manually doing it to prove that the scans were good enough over a big number of notebooks to then action getting them destroyed. And we haven't quite got there yet, but I think we're moving towards that point. But also destructive scanning might not bring the big speed increases that we all think, because you still need to spend the time taking out paper clips or staples or anything like that. And that's a very human-led job, and also the inserts are never the same size as the pages, so you still need to scan them separately. So anyway, moving on. Well, we've taken this big collection of notebooks, we've scanned a load of them in, so we have now images and images and images. And actually, this isn't really enough, because all we've done is we've moved the problem from the physical world, and we have pretty much the same problems now in the digital world. We have a little bit more metadata around it, because we say for each page, we say which book it's come from, which page number it is, and all of this sort of thing. But it's still not humongously useful, especially if they just go and sit on some server or database that's central somewhere. So we now need to start thinking about, well, labels. What are the individual tokens of information that we want to be able to get out of these notebooks so that we can maximize the value of the knowledge that they contain? And when we start thinking about these label classes, we have to think, well, what's important to you, but actually what isn't important to you as well? And that really comes out of, well, how do you want to use these notebooks downstream? Do you just want to have something that you can search automatically? Fine. But if you want to start doing things like taking molecules and structures and equations out of them to automatically process, well, then we need to start thinking about a very different setup. And again, you also need to think about what you're going to integrate this data with. Do you want it to be structured so that it can go straight into an ELN or a database? Are you combining different data sets? Are you taking lab notebooks and combining them with, let's say, the data from spreadsheets and PDFs? And so these are all things that we have to now consider now that we've got this real big archive of scanned material. And then I'll start at the end of the talk, I'll start talking about the modeling that we're doing, because we have various models for various tasks. So one of the things that we do is we segment the different label classes off the page, so the different tokens of information. And then we run OCR to try and get some of the handwriting out, and OCSR, so optical character structure recognition, to try and automatically convert the structures into chemical line notations. And then I keep sort of banging on about it, but connections with other resources. And I've sort of mentioned this already, but what structure do you need the data in so that it plays nicely with your modern tools? Otherwise, what's the point in doing all of this if it isn't so that we can use the old way of doing things with the new ways of doing things? So in our project, we sort of threw the kitchen sink at this. And we thought, right, we actually want to be able to extract every bit of information from these pages. We don't want to leave anything on the page. And so we defined all these different types of tokens or label types: date, diagram, equation, graph, molecule, page number, table, and text. And one of our reasons for doing this is that the master index that was meant to be able to tell us which lab notebook went with what person who worked in what group on what date has been corrupted. And so one of our tasks here, especially with the Southampton lab notebooks, is to be able to recreate that index so that people actually know who did what and when. And in doing so, we're going to need the names of the people that come from the front covers. It's not included here because front covers are a special case, but we need to know the metadata from inside the lab books, and that's why we break all of this down. And this pie chart on the right gives you an idea of how few labels our system needs in order to then be able to go and automatically work on the rest of the notebooks. So we reckon that 90% of the data hasn't actually been scanned yet. We reckon we've scanned about 10, maybe 10% of it, because the number of pages in each lab notebook, sorry, doesn't always have the same number of pages completed. And out of the pages that have been scanned in, we've labeled about 10% of them. So potentially just 1% of the overall data set. And as you'll see as I go through the talk, actually just with less than 1% of the notebooks and pages marked up, the system becomes very, very good at being able to understand what's in there. So here it starts to get a little bit more interesting, because now what we can do is we can say, right, we can segment different data types out from the images. And so here's an example of dates. So there were 17,000 pages containing different dates. And I think what's interesting here, and if you look on the right-hand side, is that the system finds dates whether they're written horizontally, vertically. It finds them if they have slashes or dashes between them. It finds the long forms as well. And I think that's a really interesting point, because the way that our system works is that all we're doing here is segmenting different data types out. But what it does is it basically crops that as a separate image and stores it somewhere, ready for us to be able to then do extra work on down the line. And that's really important, because it means that not only do we start taking and creating databases of similar things so that we can train very specific models on those things, but because we take this information and we have an identifier that says, well, what were the coordinates or where did it come from on the page, we can start to relate things based on their coordinates on the page. So relate similar things together without getting too technical. We can get diagrams out of these notebooks. I think this is really cool. So we have hand-drawn diagrams here that range from really nice, clear diagrams down to things in sort of the bottom left where I've literally no idea what that means. But again, when it segments it, it takes all that metadata. So even though we don't have any plans currently to do anything automatic with those diagrams, we can link people to them. So you say, okay, this came from lab book A, page 5, diagram 3. Well, we know through our work on the other information that's on that page, well, we know what chemistry is going on there. So we can flag these diagrams and say, hey, these might be useful to you. You may want to go and take a look at them. Again, starting to get even more interesting. So we can segment equations out of the notebooks. So doesn't matter if they're on plain paper or on lined paper, we can take these out and we can start doing work on them. And what I really like here is that it doesn't really matter how the equation is drawn. We've got a really nice bounding box around it to work with. And this, again, because we take the coordinates, well, then we can start to build this context up. Okay, so this is an equation, but actually we can see that there's text in the middle of them. So if there are two molecules horizontally on the horizontal plane and there's some text in the middle, well, then we can start to infer that maybe that text is important for that equation. And I think this gets really cool as well, because we can take graphs, again, similar to diagrams. We're not planning to do very much with these graphs, but we can at least flag to people that they exist. And one of the really great things about the system is it takes both computationally generated graphs, and then on the bottom right here, I think that's a graph of a DSC trace potentially. It will even find them. Now, as a philosophical question here, well, is that really useful? But we have taken the approach that we want to get everything out of these lab notebooks, and it's not up to us to decide what is useful and not. And then where I think it gets really powerful and actually really useful, individual molecules we can take out of the notebook, we can store them somewhere, and we can start, or we have started, training algorithms to convert them into chemical line notation. And you'll see that actually we get a real range of different types of molecules here. And we don't really see any the algorithm doesn't really favor any particular part of chemical space. It's very good at recognizing a molecule is a molecule and bringing it out. And I put page numbers here, less interesting, but it starts to allow us to build that metadata automatically when we start extracting these types of tokens. And tables. I think this is the final one. And I thought I'd just throw this one in there because there were 20,000 tables in 400 notebooks. And actually, we're finding not just tables with nice horizontal or vertical lines in them. We're finding tables that are quite obviously tables to the human eye, but potentially not to a computer's eye. And I think that being able to get the full range of different, tabular information out is really important, because that's often where the most interesting work is recorded. And here we have text. The count here doesn't particularly make too much sense, because we've got obviously tons of text throughout these notebooks, but I thought it was interesting to include because it shows just how much people are writing down as they go through. Since we generated these results, we've actually changed the way that we label text. We now break it down into text that is a procedure or text that it is a description. And again, because we take these identifiers that say, well, where on the page were they taken from, it's helping us to relate relevant text to the relevant part of the work that's going on. And so just as an overview, because I guess that was all quite abstract, on the left here is it's a very nice example of a well laid out lab notebook. And on the right here is what the system has managed to segment out. So we've kind of gone from a physical store of notebooks that nobody's using. We've then digitized them, and okay, we've got a bit of sort of handwritten metadata to go along with just these scores of images. And now we're at a point where, okay, we've been able to bin certain types of information into certain categories. So this is really starting to come together to be far more useful than just a cupboard full of notebooks. And just some stats here to round it off. Around 430 lab notebooks scanned, 26,000 pages. And I've put here 230,000 segmented datas. Again, that's a bit of a nonsensical figure, but I included it because it shows that just in 400 lab notebooks, there's almost 250,000 things that might be of value. And when they're sat in a cupboard, obviously we have no idea if it's of value or not. Something just to flag, I thought it was really interesting, 18 or 17,000 molecules. We might be looking at 100, 110, 120,000 molecules just at Southampton University alone in the areas of chemical space that they work in. So I think that this is something to be aware of. Obviously, we're going to do more work onto what those molecules are, or what that text means, or what those diagrams are. But just as raw numbers, it shows the volume of work that people do. And it'd be a real shame to lose it and not use it. So now for the really interesting part. As I said, we've scanned a lot of work in. We've segmented that into various different labels. And maybe something I should have mentioned is that we can tune which labels are segmented very, very, very easily. So it may be that you come with a whole load of lab notebooks and you say, hey, we don't trust any of the writing in here. We just want structures. Or it might be, we don't trust any of the structures. We just want tables or something like that. And it's very, very easy for us just to pull individual components out. But now what we need to do is we need to do OCR. We need to convert that text into something the computer understands. We need to do optical character structure recognition. So convert the structures into line notations so that we can use them computationally. And we need to, and what I think is really the holy grail here, is we need to be able to automatically structure all of that information so that it plays really nicely with all the downstream tasks. Now, with the OCR, I'm not going to stand here and say, hey, we've fixed it, we've solved it. We can turn all your handwriting into computationally understandable text, because that's just not true. It's a really, really difficult thing to do. But with our method of binning the different types or different components of the notebooks into similar bins, what we are able to do is we're able to fine tune the model based on, say, a person. So we can say, hey, we know that Amy did 8 notebooks during her PhD, 8 lab notebooks. We can find them. We can find all the text in those notebooks. We can fine tune a model to work not just on her handwriting, but on the area of chemical space that she was working on. Or it might be that she really, really was a big fan of using tables, so that we can fine tune the models to work specifically with the style of table that she uses. So we're trying to fix it almost person by person instead of one big model to rule them all. Maybe that's something we can get in the future when we've worked on enough different people's handwritings. And then again, when it comes to the optical character structure recognition, we have a humongous database now of hand-drawn chemical structures covering a huge amount of chemical space. And this is fantastic for us because combined with some of the really cool work we're doing in building up the models, we also have this amazing training data. Another philosophical point here is actually a lot of, well, not a lot, but a not insignificant proportion of structures are wrong or equations have been drawn wrong. And then is it up to us to fix them, or are we just reporting back what is faithfully what is in these books? But yeah, that's a more philosophical question here, but it sort of detracts from the point that we have these huge databases, and so we're able to do some really, really cool training. And so these are some of the results that we get. On the left here, what you can see is some hand-drawn chemical structures. These are very simple ones. They're sort of ones I came across because we generated these results quite a long time ago. We are able to do much more complex structures than this. But what I really like is there's sort of, the 3D aspect to these structures. You can see the bounding boxes that go around. That's something that's automatically generated by the system for human consumption. It's labeled what they are. It's gone through the data revival OCSR system. It's outputted as smiles, and then I've just run that through CDK. And you can see that what CDK returns is a faithful depiction of the hand-drawn molecule that was put through the data revival systems. And again, it'd be wrong of me to stand here and say we get it perfect every time. We don't. But actually, we get it right a lot of the time. And the ones we get wrong, we can do some post-processing sanitization on those smile strings, and we can push those numbers so that we really get a good accuracy. And I guess that's what's really important here is the trustworthiness of the system in faithfully returning what's down. But now that we can convert these into line notations, we can start to build databases, or it makes it very easy for us to actually use this knowledge computationally. And of course, because we can do hand-drawn molecules, we are also able to do digitally drawn molecules. So this top one, very simply, okay, fine, nothing much going on there. The one at the bottom here, I think any chemist that looks at that will know what we mean when we say that. And this is a great example because actually this is a failure of the line notations that we're using. They don't work. Smiles and inches certainly don't work very nicely with organometallic compounds and other parts of chemical space. Something that's really interesting here, and I could talk a whole talk on it, is we're actually, or one of our colleagues in the Frey group is reviving a very old semi-dead chemical line notation language. And it's a really interesting language because it deals absolutely fantastically with these pi-bonded species. And so one of the things that we are working on at the moment is, well, can we actually use that language to bring back better representations of parts of chemical space that maybe Smiles or Inchy don't work fantastically with? And then just at the very end here, we want to structure the data. As I've said, the holy grail here is, okay, we've extracted all this information, we've converted it into something machine readable. Now we need to automatically structure it. And what I really like about this and some of the work that we're doing here, especially for one of our pharmaceutical clients, is that they've said, hey, we have this ELM. And in the ELM, we've been very specific about what we want to record. And it's very different to what we've recorded in the past. Can you take the information that we've recorded in the past, or even the information that we're recording now, but in an archaic way, and can you automatically structure it so that it slots straight into the ELM? And whilst, again, not a solved problem, and it's a very, very difficult thing to do, we're getting there, and we're doing it sort of well enough that they're pretty happy with it. Our preferred output is always JSON because it's flexible, it's nice to use, nice to work with. But I'm sure going in the future, we might get a little bit more fancy and posh about this. But I think that this really is something that would be incredibly useful down the line. And so what's next for the lab notebook project? Well, there's still an awful lot of work to do in scanning all of this work in. There's still an awful lot of work to do in building up the models for sure, because we still don't get every bit of handwriting out. We make quite a lot of errors with the handwriting. There's a lot to do with the molecules, and we need to put things in better databases. But actually, what we're looking to in the future is how do we relate what was done in these lab notebooks to everything else that person did? So for instance, you could have someone that wrote or completed 8 lab notebooks during their PhD. They then wrote a PhD thesis, and then maybe they published 2 papers. Well, something that we're really interested in is what was the information loss between all of those different documents that they outputted. So what made it into the thesis that was left in the notebooks, and what made it into the literature that was left in the thesis? And I think that there's some really interesting work to be done there, just on a level of, well, why didn't they continue certain things? Did they run out of funding? Is it worth revisiting? Did it not work? I think the did it not work one is very interesting, because, okay, if it didn't work, can we extract that? And can we, and I hesitate to use the word database, but can we start to create a database of things that didn't work, either to inform people coming through the group after them, or to start training some actually really useful ML or AI models, whatever you want to call them, that aren't just fed data from positive results? Can we start feeding them data from negative results? And are those negative results in the mostly in the lab notebooks? We're not quite sure yet, because we've not got there, but I think that would be a really cool next step, and there's some really nice things to come out of it. So thank you very much for listening. My contact details are here. Please feel free afterwards to contact me if you have any more questions. I'm always up for an interesting chat. And on that note, thank you very much. Up for some questions now.
Cool. Thank you very much, Sam, for a very interesting presentation. So as Sam said, we do have time for some questions now. You were bang on the time that you said you were going to be in terms of delivering the presentation. So we can take any questions through the Q&A functionality or directly through the chat. Hopefully people should have those accessible to them. I did have a couple of questions, and now my mind has gone completely blank, and I've completely forgotten them. So yeah, I was wondering about potentially about some of maybe the intended use cases. So obviously you've talked about extracting a lot of this information from it. What you talked a bit about, like, larger scale kind of into the future. What are your kind of intermediate steps for some of the data that you're getting out of specifically potentially the Southampton lab books, let's say?
Yeah, I think that's a really interesting question. And the crazy answer is we're not quite sure. And I don't think anyone's really quite sure, because no one's really gone back and looked through these resources. And we're starting to get so much information out of them, that it's almost an information overload type scenario. And so, as much as I hate to be speculative, I think that some of the real use cases will fall out in the future as people start to have access to the information and use it. To be more specific, when we are working with some of our non-academic partners, there are 2 things that people are really keen on. One is they really want to use machine learning, and they really want this data to be able to come forwards and inform the really state-of-the-art models that they're building and deploying at the moment. And the other thing is, as I sort of alluded to in the chat, in the talk, they don't want to lose the information, as in they're implementing these fancy brand new systems, and they want to pre-populate it with the old knowledge. And I know that's not really a use case, but it's kind of what people are talking to us about this. But for me, I think that just being able to search them, not lose the information. We have a real problem with people leaving and taking knowledge with them. Especially what they do is they take where to find that knowledge with them. We want to be able to help with that, and basically just getting it into a format that works with modern systems. So that, yeah.
Excellent. Well, that has given the audience enough time to type some questions into the chat. So there's a couple, I think, in the Q&A. First one is a question to say, why weren't you happy to mention the word database?
So database, great things. I don't really want to get into the game of databasing. And I understand that sounds very counterintuitive given what we're doing. But for two reasons. One, in the academic world, I love this idea of, okay, we can come in, we can get your information, and we can give it to you to do with as you please. I don't want to be the person that puts it behind a paywall or puts it and hosts a server or something like that. That's why I'm a little bit hesitant there. And certainly in the other work that we do outside of academia, of course, we're building databases. I know it's really daft, but I like the idea of, hey, we don't want to trap you into a way of working. We want to liberate this information and give it to you so it can go into, say, your database, not my database, or your schema, not my schema. That was all I was getting at there.
Excellent, thanks. So there's a longer question in the Q&A, so I'll potentially break this up into two parts. Exciting project. Interested to know where the data is being stored. So how secure it is and how will it be preserved / where?
So yeah, to that question, we are working with our iSolutions team at Southampton University, and they have a number of long-term sort of tape storage options, and that should be able to keep it preserved for an awful long time. Very sorry that I can't answer too much about it, because we've only just had enough of the information come through, and we've only just been able to say, right, this is a good thing to do. So now we're thinking about the long-term storage. Maybe we should have set that up to begin with. But I know that there are things that you can do here. And I know with AWS as well, we looked into, you can get tape storage. It might take you 7 days to get the data out, but actually it's specifically designed to persist for a long time, and it's backed up in multiple locations and all that sort of thing.
Yeah, I mean, there's quite a lot of I guess different discussions around kind of, backups and keeping things accessible, but also being able to sort of get to them as and when you need them, making sure only the right people potentially can get access to them, and like all sorts of different angles. So I guess watch this space for further developments on the discussions around that. So a question around the cost, about how much the scanning costs, so potentially across either using the phone app or the scanner, and how it's being funded, and I guess the particular app. So I guess that was the link to the Microsoft scanner. Maybe see if I can find a link.
Yeah. So our Southampton University Library are fantastic people, and they gave us a fantastic deal on getting all of this scanned. I think it was somewhere around £10,000. When I approached some outside commercial vendors to do this, actually the price varied wildly. And I might go back to them now we know a little bit more. And so to get it destructively scanned, I think we were looking for the whole lot, so 12-ish terabytes of data potentially. We were looking at around the £20,000 mark. To get it non-destructively scanned, like the library are doing for us, with a commercial vendor, that price just went through the roof. So yeah, there's certainly some considerations there, but there are, well, we found a way around it, right, using our library. There are ways around this, and I think actually scanning costs are coming down, which is an odd thing to say, but I saw something recently where at a conference I went to where someone had a way of scanning that was new, and they were saying that it was cutting costs by 60%. So sort of read into that what you will. The phone app, horrendously cheap. I must have paid for it with my Microsoft subscription, so maybe £6 a month, and then you get as many scans as you want for no money. And actually it's really, really good. I scanned, I don't think I said this in the talk, I had 7 200-page lab notebooks. So there were around 15 or 1600 scans. And okay, it took me, I think, 4 or 5 days of my time, and they were awful days. But actually, I managed to get 7 entire lab notebooks scanned in around my day job, just every time I had a spare minute, just going through and taking the photos for very little money.
I assume that is Microsoft Lens, isn't it?
Microsoft Lens,
yes.
Yeah.
Okay, I'll put the link into the chat. So there's a Google Play app and an App Store app. So we have a question, same question, I think, or similar from 2 different people, around protecting kind of IP or sort of handling the intellectual property aspects of it. Kind of how I'm assuming you have encountered potentially issues around that, and how you've sort of been handling some of that so far.
Yeah, so I think the first thing to mention here is that every single data set is separate in the system. Okay, so there's no overlap. Models aren't trained across client data and then deployed on other client data unless we've been specifically told that we can do that. So we have these base models that know a lot about a lot, and they've been trained on data that we are allowed to train on, and then we fine tune on each of our clients' separate data. That's how we work with them. There's an interesting query around, well, we're using all of this UOS lab notebooks and we want to give it back. And then there's some of them are still embargoed. So that's going to be an issue that we're going to have to go through, and we're working on that at the moment. When it comes to finding new bits of IP in these notebooks, we have done that with a client. And that's just, obviously, you just give it straight back to them, and it's hands off from us. So I don't know if that particularly answers your question that well. It's one of them where we're still working through this. But I think the real thing to say here is that unless we've been explicitly enabled to, we don't cross-train on data sets. Data sets are kept separate. Only very, very specific people allowed access to those data sets, and things like that.
Oh, thank you. So the next question, we've got quite a few questions lively in that. So what are the main challenges you see around linking the information you find on all the lab notebooks?
So one challenge is that if the information is wrong, what do we do? So if the molecule has been drawn incorrectly, it's just not a valid molecule. That's a challenge. And we get around that by putting flags in. So we say, hey, look, this doesn't make any sense to our system. And then that goes through a process. Is it our system messing up, or is it that it genuinely doesn't make sense? So we give that problem back to the person in the loop. Another issue in linking information we find in the lab books is, as I sort of said, in our experience, the indexes are not as good as you would hope, and in our experience, they're corrupted. So we kind of have to start from first principles. We don't have a master document to check against, and then we're very much relying on how good the system is, and actually we're also relying on how good the person who filled that lab notebook in is at being a professional and putting the information down. Then you get into the potentially more interesting challenges. So how do we link different projects together based on a parameter? So that could be, well, is someone that works in this side of the department, is someone works in this side of the department, they're not working on the same thing, but there's actually overlaps maybe in the chemistry that they're doing. Well, then that's then a sort of a natural language processing problem or a cheminformatics problem. And that's something that we're also working on. We're not as far down the line with that as we'd hope to be. But there are things, I mean, I'm sure everybody here has probably heard of like Chem Data Extractor. They've done an awful lot around NLP for chemistry, especially with all the language transformers that are coming in as well. We're experimenting with them to try and relate those separate areas. But to sort of answer your point directly, I actually think it's, and this sounds awful, it's how do we deal when the information is just plain wrong or not professionally put in there? They're the real issues.
And there's a kind of a follow-up question to that, I think, which is about linking, are the theses or reports linked to their lab book numbers anywhere, or just not at all?
Yeah, no. Mixed bag, not really. We have done some work recently where I can't remember what the database is called that they're all meant to be in. We were really excited about it, and then it turned out that they just weren't there. But we have gone to the department, and we've got a list of people that have worked in the department and who their supervisors were and when they worked here. And that's a great sort of ground truth, because then we can try and relate the theses to the reports via name, so some sort of identifier. The problem with linking to the lab notebook numbers in our particular case is that, as I said, the index has been corrupted. So someone's taken one of the columns on the spreadsheet and it's been completely mixed around, and we don't know why. I'm sure in other institutions that might not be an issue, basically. But for us, it certainly is. But yeah, we really try to start from sort of the first principles. What can we take off the page? Okay, we can take page number, we can take date, we can take the title, we can take the name of the person, we can take what the lab notebook is, our own sort of identifier there. That's a really great 5 pieces of great metadata that enable you to go forwards and find, okay, well, this was their thesis, this was the literature, all those sorts of things, and be able to relate the different information to those different documents.
That actually links probably very nicely into this next question. So obviously you just mentioned metadata there that you're capturing. So this question asks about the metadata that you're capturing when you do a scan of the page. So obviously you just mentioned some metadata. Is that all of the metadata that you'd capture, and would you capture that on every single page?
Yeah, so for the note for this project, yes, we capture all of that metadata and more. I guess you get into a conversation of what constitutes metadata, but we also capture an identifier around what position on the page that bounding box is. So what are the coordinates of it? So where does it relate to the other information on the page? I think that's a really, really interesting piece of data to capture. And then the guys doing the scans. So again, can't speak highly enough of the people in our library. They are filling out a spreadsheet of interesting stuff to do with each book. So I can't give you any examples off the top of my head, but the guys that are, as I said, scanning them through, we collect all of the metadata in our system, and they're collecting interesting facts about each book as we go along, which are saved and then are able to be appended in there. So I think another bit of metadata we can capture, but we haven't yet, is the name of the supervisor and the group that they're working in. Again, is that metadata? I'm not sure, but it's certainly some sort of identifier that helps us in knitting together this graph of different information and knowledge.
Cool. So we've got a question here that says, what are the issues involved in cutting up the notebooks into loose pages so they can be put through a sheet feeder?
Yeah, great question. One, people don't trust that, or haven't trusted that the scans would be good enough. We've had to do a lot of work and go to a lot of different people, and are going to a lot of different people at the moment, saying, "Hey, look at these scans. Look how great they are. Compare them to the notebook. They're great. You know, we don't need to keep these notebooks." So that was one issue. Another issue is that even if you put them through a sheet feeder, you need to pull out all of the staples. So our notebooks have things stapled into them, paper clipped into them, glued into them. They have things sellotaped into them. You still need to do that human manual process of taking all of those things out before you can put it through the sheet feeder. And then you have a bit of a headache, because often the inserts aren't the same size as the sheets of the notebook. So then you have to take them away and you have to scan them manually anyway. So for one of the data sets that we have that isn't this Southampton University data set, I think that there were on average 3 inserts per page. So actually you can automatically scan the notebook. That's only a quarter of your job done. You've still got to manually scan everything else, right? And actually, I guess that potentially it is for IP reasons. Looking forwards, again, it comes back to this distrust of destroying the notebook, because we still want to have the physical one there. So yeah, hopefully that answers that question.
Oh, and we've probably got time for just one very quick last one, and then I think we've actually got through all the questions. So are the scans checked by a human to catch any bad imaging?
So there are a couple steps here. When it comes to literally physically scanning it, then yes, every single scan comes up in front of you. So whether you're using the professional piece of scanning equipment that literally comes up in front of you, and they've got nice grid lines and bounding boxes and things like this for you to check against. When you're using the phone app, you can see in front of you immediately as you take it. And as with all these things, before they let you save the whole set of scans that you've done, it makes you go through and check. So there is a visual check there. When it comes to segmenting the information off the page, we used to do a lot of checking. We used to check every single bit. We put those bounding boxes on the page and we'd go, right, that's not right. This is right. That's correct. But as we've got better at this, we're starting to see over 99.9% of percent accuracy in being able to, in the system, not only creating the bounding box around the token in a sensible manner, but labeling that bounding box the correct thing. So actually, we're doing less checking now. When we have new bits of data come through, yeah, we always want to check because it's just interesting to check that it works on this new person's information. But with the US notebooks, we've still probably got potentially 2 and a bit thousand notebooks to go, and the checking is plummeting because we trust it. When it comes to the automatic conversion, so handwritten text to computer text, or hand-drawn molecules to computer molecules, humongous amounts of checking, because even though we're pretty good, we're not perfect. And so actually the checking comes from a selfish place, because anything that's wrong, we want to catch, put back through the model and retrain it. So there are different stages to the process, and at each stage we have various different amounts of checking.
Oh, well, thank you very much. So I probably will very quickly just wrap up. So I'll just share my screen again. So thank you very much to Sam for giving an excellent presentation, to all our attendees for asking some excellent, very lively questions. Our next webinar is scheduled on Thursday, the 14th of December. One final webinar before the end of the year about data to knowledge. So this is machine learning applications for interatomic potentials. So you can find out more about that on our website. But you can also find out about what we're doing on social media. So on Twitter, on LinkedIn, and also you can follow our YouTube channel where this video will be posted when it's been edited. And you can also join our JISC Mail mailing list on our website via the footer. So here is a quick selection of our social media things. But yes, just a massive thank you to you all for being here today. And thank you for Sam for such a wonderful, engaging presentation. And I hope you all enjoy the rest of your day. And we'll see you soon at another webinar, hopefully.
Thank you very much, everybody. It's been great.